Hello everyone. This study, electron energy can oscillate near a crystal dislocation, is all about a different approach to study the electronic properties in the presence of crystal dislocation. We first introduce the concept of dislocation and other approaches to study the relevant electronic properties, and then we'll focus on our approach by quantizing the dislocation itself, which is named a dislon, and we'll discuss its features and predictions. A dislocation is a type of crystallographic defect caused by applied shear stress. There are two basic types, edge dislocation and screw dislocation. There are already plenty of approaches to study the electronic behaviors in the presence of dislocation, such as potential modeling, treating the dislocation's potential scattering with an electron, or general relativity, which treats the dislocated crystal as incurved spacetime, or density functional theory, which can predict the ground state properties in a large supercell. And in our approach, we quantize a dislocation itself. The reason is the following. Dislocation classically contains both strain field energy and this local vibration, since it is mobile. So the classical Hamiltonian contains both kinetic energy and elastic potential energy. After a canonical quantization procedure, the classical Hamiltonian can be quantized by this simple form, which we call a dislon instead of a phonon, since it exists only near a crystal dislocation. This dislon Hamiltonian contains both this strain field energy and this quantized vibration. First, we know that a dislon, as a type of quasi-particle, has its own excitation spectra. Compared to the linear dispersive shear wave, these terms are the quantum mechanical corrections caused by the topological constraint of the dislocation's definition. And using this quasi-particle dislon, we can treat the electron dislocation scattering from a many-body perspective. So this is the electron-dislon interaction Hamiltonian, from which we could compute the electron-dislon interaction relaxation time. Here we use one-loop approximation, and resulted relaxation time is consistent with the semi-classical results. But here, using the dislon theory, we could compute relaxation time's position and momentum dependence instead of the only simple average, as the case of semi-classical results. Using this theory, we predict that the electron energy could oscillate near a dislocation. Compared with the classical screening, like Thomas Fermi screening, which is screen the Coulomb potential, or the quantum mechanical screening, like Friedel oscillation, which is the charge density oscillation. So here, it is the electron energy oscillation, not a density oscillation. And such energy oscillation can occur even at the presence of a single electron near a dislocation core. No need for a bunch of electrons, as the case of Friedel oscillation. To summarize, this dislon theory is about a quantum field theoretical description of a crystal dislocation, and we believe it provides plenty of opportunities to study the influence of dislocations on material electron transport, phonon transport, superconductivity, and classical and quantum phase transition. Thank you for your attention.